Good day. This is a continuation of the lecture on Unit 3-2, Response Surface Methods. In the first part of this lecture, we talked about these steps in the method of steepest ascent or descent. Okay, so the shapes with green border have been discussed already. So fitting a new first-order model, moving along the path of steepest ascent for the first order model, and then determining when the first order model is not adequate anymore. Okay, so from there, we move on to fitting a second order model and analyzing the second order model, and after which locating the stationary point. Okay, so as I mentioned in the previous lecture, when you're close to the optimum or within the optimum region, the second order model usually suffices. So the first order models start to become inadequate, and usually the second order model suffices or is adequate. Okay, and the goal basically is to determine the optimal operating conditions. Okay, so for example, or that means that you want to find the values of the independent variables, the x's, that will optimize the response y. So this is the general form of a second order model. Okay, so you have the quadratic terms and the interaction terms added to the linear ones. So as I said, after you fit the model, you can start analyzing the model and locate the stationary point. Okay, so the stationary point is basically the set of x's for which the partial derivatives is equal to 0. Okay, so this stationary point, could represent one of three things. It could be a point of maximum response, a point of minimum response, or a saddle point, or what you call the minimax. Okay, so this is how a response surface with a point of maximum response looks like. Okay, and this is the corresponding contour plot. So as you can see, as you move towards the sort of center, the response increases. All right, and this would be the response surface for and the contour plot for a model with a point of maximum response. Okay, so as you can see, the pattern is opposite with respect to the contour plot. So as you go inside, the response decreases. Okay, and this one, is an example of how a response surface with a saddle point would look like. Okay, so you actually have minimax here. So as you can see, you can identify where the direction, where you have maximum response, and the direction where you would have minimum response. Okay, now to analyze the second order model, we can it would be easier for us to tackle the analysis of a second order model in matrix form. So the second order model could be expressed as such. Okay, so y hat, y hat is equal to beta naught hat plus x prime b plus x prime b x, where x is a k/1 matrix of your independent variables. B is a k/1 matrix for your first order regression coefficients, and capital B here matrix is a k/k matrix for which the main diagonal constitute the pure quadratic coefficients beta I, and the off diagonal are 1/2 mixed quadratic coefficients. So these are the beta ij where I is not equal to j. Okay, now we proceed to determining the stationary point. So you can determine the stationary point by satisfying this condition that the partial derivative of y with respect to x is equal to 0. Okay, so in matrix form, you can express it as such. From the previous slide, we know y. Okay, so we get the derivative of y hat. Okay, we know y hat, and okay, so that is this one, and we get the derivative of this with respect to x. Okay, and equate that to 0. So the derivative of y hat with respect to x is just this one, okay, equal to 0, and therefore our stationary point, okay, x sub s, is equal to negative 1/2 beta inverse, b inverse, I should say, times b. Okay. And now we substitute this expression, okay, in this equation. And by doing that, we could get the equation in order to predict the response at the stationary point. So y hat s is equal to beta naught hat plus 1/2 x prime s b. Okay. Now, of course, you would want to characterize the response surface, no, after determining the stationary point. Okay, so when we say you want to characterize the response surface, you would like to know, okay, whether the stationary point is a point of maximum response or a point of minimum response or a saddle point. Okay, you might also want to know, okay, or determine the relative sensitivity of the response to the independent variables. Okay, so these are things you would want to know when you are characterizing the response surface. Okay, now to characterize the response surface, the method called canonical analysis is very useful. So in order for you to be able to do that, the first thing to do is to transform the model into a new coordinate system. Okay, and to do this, first you want the origin to be at the stationary point, and then second, you rotate the axis until it is parallel to the principal axis of the fitted response surface. Okay, this is an example for two-factor design. And then after that, you obtain the canonical form of the fitted model. Okay, so the canonical form of the fitted model would be y hat is equal to y hat s plus lambda 1 w1 squared plus lambda 2 w2 squared until lambda k wk squared, where w sub I, okay, the set w sub I are the transformed independent variables, and the set of lambda I are constants, okay, which are basically the eigenvalues of the capital B matrix. Okay, so you know how to do this from engineering mathematics. But of course, this is already mostly done using statistical software packages. Okay, so back to characterizing the response surface. Once you get the canonical form of your model, okay, you will now investigate, or okay, after getting the canonical form of your model, you now look at the eigenvalues, okay, because looking at the eigenvalues will tell you something about what kind of stationary point you have for this model. So if the eigenvalues are all positive, then that means that the stationary point is a point of minimum response. If it's all negative, then the stationary point is a point of maximum response. And if they have different signs, then the stationary point is a saddle point. Okay. Moreover, the surface is steepest in the WI direction for which the absolute value of the eigenvalue is the greatest. Okay, so for example here, if say that your lambda 1 and lambda 2 are both negative, then you would know that XS is a point of maximum response. And then say that W1, lambda 1 is greater than, the absolute value of lambda 1 is greater than the absolute value of lambda 2, then the surface is steepest along the W1 direction. Okay, now let's go back to the chemical yield example. Okay, so from the last lecture, we stopped at a point where the first order model is no longer adequate for the data. Okay, so as you recall, the next step is to conduct further experiment and fit a second order model. Okay. If you just stick with this data, a second order model cannot actually be fit either. So further experimentation is needed. Okay. And for that, we use this, in this particular example, the central composite design is used. Okay. And this is one of the most popular experimental designs for fitting the second order model. Okay. So for this example, okay, this is how the central composite design looks like, okay, graphically. And basically, we augmented the original experiment with 4 additional points, okay, 4 additional runs, okay, where our coded variables would have the value x1 is equal to 1.414, x2 is equal to 0, and then x1 is negative 1.414, x2 is equal to 0, and then x1 is 0, x2 is 1.414, and x1 is 0, and x2 is negative 1.414. Now, these are translated to the natural variables, which are then these values, okay? And suppose that these were the responses that were observed by the engineer who was conducting this experiment. Okay, now note that we assume here that the engineer ran the additional runs about the same time as the original experiment. And we assume this because if this were not true, then blocking would be required, no? Okay, you can also notice here that there are 2 other responses, but for this example, let's stick with the first response first, which is the original response we were interested in. That is the chemical process yield. Okay, now, okay, so this is an excerpt from Design Expert Output presented in Design and Analysis by Montgomery. Okay, so again, the response is yield. And you can see here that there's a warning that the cubic model is aliased. Okay, so there is a significant aliasing in the cubic model. And that's mainly because we don't have enough data also to be able to fit a cubic model. All right. And you can see here that the sequential model sum of squares or extra sum of squares was performed. So you can see the analysis of variance for linear, 2-factor interaction, quadratic, cubic models. Okay, and owing to the fact that the p-value for the quadratic model is very small, and you can see that for the others it's actually very high. It is recommended that we take the quadratic model. Okay. Okay, and then there's also a part in the Design Expert Output on lack of fit tests. Okay, and basically you want the selected model to have insignificant lack of fit. And as you can see, the cubic and the quadratic, okay, would have insignificant lack of fit, okay, at say 5% significance level. Okay, however, we note that cubic is aliased, so the quadratic is again suggested based on this test. Okay, and then this is the model summary statistics. All right, so we, as suggested here, we focus on the model minimizing the press, or equivalently maximizing the predicted R squared. Okay, and as we can see, the quadratic model has the highest predicted R squared. Okay, so for the quadratic model, this is the ANOVA. As you can see here, we have the terms, the linear terms, and then the pure quadratic, and then we have the interaction. Okay, and all of which are significant at 10%. Okay, and the square, the quadratic, and the linear are significant at 5%. Okay, and of course the model is significant as well. Again, looking at the R squared, it's actually very high. Adjusted R squared is not too different from the R squared. Okay, and the predicted R squared is also very high. Now, please review from the previous lecture what these imply. Okay, and then here you have the coefficient estimates, degree of freedom, standard error, and then you also have the confidence interval, 95% confidence interval, and the VIF. Okay, so this is a measure of orthogonality. All right, and now we have here the final equation in terms of the coded factors. All right, as well as the actual factors, the normal values. Okay, the normal variables. Okay, and this is the corresponding contour plot and response surface for this particular example. Okay, so as you can see, if we just investigate the contour plot, okay, you can already see that this seems to be a model with a point of maximum, maximum response. So as we go inwards, you have a higher response. All right, and also as you can see, it appears that with the spacing of the rings of the contours, it seems that the response, which is yield, is more sensitive to time, reaction time, than to temperature. Okay, reaction temperature. All right, so we have that. Now, okay, so going back to our algorithm, we have fitted a second order model. Okay, the next step is to locate the stationary point. Okay, locate the stationary point. Okay, and to do that, again, we can perform the calculations using matrix mathematics. Okay, again, our B here are the first order regression coefficients, and our capital B here is this one. Okay, so pure quadratic coefficients are along the main diagonal. Okay, so from that, we have these values for these two matrices. And then x sub s, as we know, is equal to -1/2 capital B inverse times small b. And this would be equal to -1/2. Okay, so inverse of this matrix times inverse of this matrix times this matrix, and we get this matrix. Okay, which means that our stationary point consists of x1 equals 0.389 and x2 equals 0.306. Okay, and translating that to the natural variables, we use this equation, and we would get, in terms of the reaction time, 87 minutes. And the reaction temperature would be 176.5 degrees Fahrenheit, about that one. And the response at the stationary point would be Ys hot is equal to 80.21. Okay, so we have located the stationary point. Okay, so we can end there, but in most cases we want to analyze further. So, we translate the previous model in canonical form. Okay, and okay, so we basically want to get the roots of the determinantal equation. Okay, and this would be the determinantal equation. Taking the roots of the determinantal equation would actually yield the eigenvalues. Okay, so the determinantal equation would be this one. Okay, and we know B, and of course we know I. This would turn out to be this matrix, okay, for our example, and we equate this to 0 to get the roots, and we get, okay, so again, lambda 1 and lambda 2 for our example are the roots of this equation. And from here, okay, we get this equation. So lambda squared plus 2.3788 lambda plus 1.3639. Okay, and the roots of this equation are as follows. Lambda 1 equals negative 0.9634. Lambda 2 equals negative 1.414. Okay, so then we can now use this in the canonical form of the model. So y hat is equal to 80.21. So this is y hat s. Okay, minus 0.9634 w1 squared minus 1.4141 w2 squared. Okay. Okay, so looking at this, we can now perform, now having obtained the canonical form of our model, we can now perform canonical analysis. Okay, and looking at the eigenvalues, they're both negative, which means that the stationary point is a point of maximum. Okay, and we can see that the absolute value of the eigenvalue for lambda 2, okay, is greater than that of the absolute value. So this should be absolute value for lambda 1. Okay, therefore the surface is steepest along W2. Okay, now the relationship between the canonical variables and the design variables is handy when the optimum point is not operationally feasible due to several reasons. So for example, if it is excessively costly to operate at the stationary point, okay, so we want to know, okay, the relationship between the canonical variable and the design variable, and we can do that using this analysis. No? So W is equal to M prime times the quantity X minus X sub S. Now, if Mi is the ith column of M, then Mi is the solution to this. Okay, so B minus lambda I times Mi is equal to 0, for which the summation of Mji squared from j equals 1 to k is equal to 1. Okay, so let's illustrate that in an example. Okay, suppose that it is excessively costly to run the process at the stationary point of 87 minutes and 176.5 Fahrenheit. Okay, these are the values of x1 and x2 at the stationary point. Okay, from canonical analysis, yield loss is less sensitive to W1 direction, right? So for lambda 1 is equal to negative 0.9634. Okay, so we start with lambda 1 here because we saw that the yield loss is less sensitive to the W1 direction. Okay, so for lambda 1 equals negative 0.9634. So we go back to this, no? Then we would have this. Okay, so we go back to this, right? For lambda 1 equal to negative 0.9634, we would have this matrix. Okay, so this would be the B minus lambda II matrix. Okay, times M11, M21 is equal to 0. Okay, then we would have these equations. Okay, we let M11 squared plus M21 squared be equal to 1. Okay, and let's let M21 is equal to 1. So we arbitrarily set M21 star is equal to 1. So we find M11 star is equal to 0.3027. Okay, okay, and then we take the square root of M11 star squared plus M21 star squared. Okay, so we normalize it. And so we get M11 equals M11 star over 1.0448. Okay, so that is results in 0.2898 for M11, and for M21 this is equal to 0.9571. Okay, so we do the same thing for lambda 2 equals negative 1.4141, and we would obtain M12 is equal to negative 0.9571 and M22 equals 0.2898. Okay, so that would be the second column of the M matrix. Now from there, okay, we would know the relationship between the W and the X variables. Okay, so we go back to this. Okay, W is equal to M prime times X minus X sub S. Okay, so since we know M, okay, this we can take the transpose of M, okay, multiply that by the matrix X minus X sub S. Okay, so we can then get the relationship between X and the W variables. Okay, so this would be the relationship between the W and the X variables. And so this would help, this would guide us in moving away from the stationary point, okay, in order to, say, for example, minimize cost, okay, without compromising too much the performance in terms of the response variable. Okay, so what if you have multiple responses, if you're dealing with multiple responses? So, of course, first thing is you obtain the response surface model for each response. Okay, and then after that, you find the set of operating conditions that optimizes all the responses, or at least keeps them in the desired ranges. So let's go back to our chemical process yield example. As I mentioned earlier, there were two other responses that were obtained. Okay, so say for example, the engineer is also interested in viscosity and molecular weight. Okay, and say that she was able to obtain the following second order model for viscosity and molecular weight already. Okay, now in terms of the natural variables, this would translate to this. Okay, you can take a pause to appreciate these two models better. Okay, and this would be the corresponding viscosity contour, the contour plot for viscosity, and the response surface for viscosity. Now, investigating the contour plot, it looks like we have a point of maximum response here. Okay, and that becomes more obvious with the response surface. And then we have a first order model for the molecular weight. And then this one, as you recall, is the response surface and contour plot for the process yield. Now, with experiments that have a low number of design factors, so say for example, K is equal to 2, overlaying the contour plots, okay, is a useful technique. Okay, so let's show that first. But take note that this becomes awkward or cumbersome, okay, if you have more design factors, okay. Now, suppose that in our previous example, the chemical process yield example, suppose that the following are important conditions that must be met by the process. So, the yield should be greater than or equal to 78.5. The viscosity should be greater than 62 and less than or equal to 68. The molecular weight should be less than 3,400. Okay. Now, if you overlay the contour plots, okay, looking at these conditions, this would be how the overlaid contour plots would look like. Okay. And you have a bigger region, okay, optimum region here, and another optimum region here, okay, and a smaller optimum region here. Okay. So again, you can pause the video to appreciate this graph better. Okay, you can go back to the slides where you have each of the contour plots for yield, viscosity, and molecular weight, and determine which ones, okay, on this graph correspond to each of those responses, okay, and why these two regions are the regions of optimum. So with this, then the engineer can choose the operating conditions within these regions in order to satisfy these important conditions. Okay. Now with factors, with experiments with higher number of design factors, it is more advisable to use mathematical techniques to identify the optimum regions, okay? But that is a topic for more advanced stat courses. Okay, so this is where we end for our discussion on response surface methods. For this lecture, we covered the following topics. For this unit, we covered the following topics. We talked about the general procedure for performing RSM. And then we also talked about the method of steepest ascent or descent. We also covered canonical analysis and talked about multiple responses. So that is the last lecture for this semester. Feel free to go back to the previous lectures in order to refresh yourselves of the earlier topics. Okay, and if you have some questions regarding any of the topics that we have covered so far, feel free to email me or send a message over Ovle. And also remember to finalize your course projects. If you have some questions, you can always contact me and set an appointment. With that, we were able to cover all the topics for this course, statistical design and analysis for engineers.